Hi, and welcome back to Gaffy's Grinds. In this video, we are going to discuss something called a standard solution. Now, we're going to discuss standard solutions, and in the next video, we're going to build into discussing a mandatory experiment that we have to do about how to make one of these things. So we're just going to begin by talking about that sometimes when chemists want to do analysis, they will make solutions where they have a solute like this. Okay, so the solute. And they very accurately measure the amount of solute they have. So for example, they might accurately and precisely measure that they have 16.10 grams of this solute. Now, of course, they could do this with any solute, but there's reasons why some of them aren't suitable for this, which we'll see later on. So just focus on for a second that we have an amount of solute that we very accurately and precisely weighed out. And they then take that solute and they use it to make up a solution with an exact known volume. So they take that solute, they add it to water, and they make a solution with an exact, precisely known volume, so 0.25 liters. So the volume, not only is the mass or the quantity of the solute known, the volume of the solution is accurately known too, volume of solution. The key thing here that's different from what we've talked about before is that we're saying that this here, which is the number of grams of the solute, and this here, the volume of the solution, are very accurately known. The only way you could get these to be very accurately known is if you measure them very precisely. Now, of course, we've seen the equation before where we know that if you know the quantity of solute, and you know solution, work out. So quantity of solute over quantity of solution will give you the concentration. What we're saying is that a solution like this, the concentration is very accurately known. You know precisely, exactly the concentration, very accurately known. Now, chemists have a very special name for this type of solution. They call it a standard solution. So this here would be a standard solution. This is when the scientist or the chemist knows the exact quantity of solute because they measured it very precisely, and they know the exact quantity of solution because they measured it very precisely. We call this a standard solution. Okay, so at this point, that is a definition. As you can see, it's written in red over here. So what I would like you to do now is make a note of that definition. Pause the video and do that now. Okay, so you'll notice if you're new to the channel, you notice that I don't just say, this is the definition of a standard solution, take it down and move on. We build up to it. We build the idea up to the definition because definitions don't mean much by themselves. They're a nice summary of what you should have learned already. So that's why we build it up using everyday language that you guys should understand. And we build to the definition. For me, that's the best way to help students to learn stuff like this. Now, the next question is, why would we bother doing that? Why is a standard solution actually useful? Okay, so let's say we have made a standard solution. So the big question here is, why would we bother? So let's say we have a solution here, it's this red one, and we know very accurately we have made a solution that is 0.12 molar, 0.12 moles per liter. We know it's exactly that concentration. We'll call this solution A. So why and how is that useful to us? Well, it's useful to us because what we can do is we can take this solution and we can then find another solution that is an unknown concentration. We don't know how many moles it is. And this happens to be a solution that will react with solution A. So let's say that solution A was an acid, then maybe solution B is a base or an alkali. Those two things will react together. So long as they react, then there's something we can do here. Okay, we'll call this solution B. So we know the concentration of A very accurately. We do not know the concentration of B. But what we can do is we can do a very precise chemical reaction where we measure exactly how much of A we used. So say we measure by finding out how many liters of A it takes to react with solution B, how many liters of this. We can use these numbers, we can use these three numbers, the amount of A, or sorry, the concentration of A, the volume of A that we used, and the volume of B, and then we can calculate the concentration of B. So what we're doing is we're getting a chemical reaction between A and B. We're measuring the volumes that it takes for them to fully react. And then we can calculate concentration solution B. This is a very precise and accurate type of experiment, which is called a very common chemistry experiment, where it's basically an analysis where you can use something, a solution that you do know the concentration of, to find the concentration of a solution that you don't know. Okay, so very clever, simple calculations can help us to work that out. Once we have then found the concentration of B, so say we do this sum and we find out that this is actually 0.25 molar, we work that out. Well, we say that now solution is standardized. So it has been made standard compared to the standard solution. Remember, this one is standard because we actually made this up. We accurately made this up. Sorry, not standard. This is a standard solution, the red one. We actually made this with an exact amount of grams in an exact amount of solution, and then we used it to find solution B. So we say that we have standardized B. Now, is it as accurate as A? Probably not, because things can go wrong in the titration, but it's going to be pretty good. Okay, it's definitely not as good as A, but it's still a very, if you've done it right, it should be a very close, to the real concentration. Of course, what could you do? You could then take solution B and do solution C. So you could have another unknown over here. Again, unknown molar. This is solution C, and we could use B to find C. So long as it's a solution that reacts with B, we could do that way. And then we would standardize C. And again, it would become a little bit less accurate every time you do this, but still very clever and very intelligent way of doing this. Who would use this? Many scientists would use this, forensic scientists, if they're trying to find out what concentration of blood or what concentration of different chemicals that they found at a crime scene. But also anybody in the pharmaceutical industry, if they wanted to know if they've made a solution up, they wanted to know its concentration, they would do a titration. Okay. Now, often when you get to high levels of chemistry, it's really machines that do this. You put the liquids in, and the machine tests them, does a quick titration and figures it out. But we will be learning how to do it manually. We've got about 8 titrations on the course, or is it 8 or 9? I think we'll be doing 7 or 8 of them coming up. We might get a few done before the summer, hopefully. But yeah, before we do that, we need to know how to make a standard solution. So I don't want to lose that picture here. Okay, so that is why we would want to make a standard solution, so we can standardize other solutions. Okay, all right, so on to then making the standard solution. Can I just use any solute to do it? The answer is no. Not all solutes can be used to make a standard solution. Remember, keep the idea of standard solution in your head. The big picture here, standard solution, is it's a solution whose concentration is accurately known. You know exactly. So why are some solutes not able to do that? All right, let's take an example here. So let's say we had a pile of solute here. We've measured it out. And let's say it's 10 grams. So we've got 10 grams of a solute. And we want to dissolve it in some solution. We're going to add some water until it goes up to an exact quantity. The issue here is that this solute is black. Just example, just imagine all the particles are black. But mixed in with it are some of these little red particles. Now, there's only a few of them, but they're a different substance to what the black is. We say that this substance has a different substance mixed in with it. Okay, and the word we use to describe this, we say that this substance is not pure. Now, if it's not pure, then the 10 grams is not the substance that you want. So if you go ahead and mix it in and add it, go ahead and mix it in, dissolve it up, that's fine. You can then think, oh, I've got 10 grams of my solute in 0.25 liters of solution, but you don't. You have less than that, because some of the grams are the red particles. So it might be only 9.8 grams that are the black particles. Now, that might not seem important because it's only 0.2 grams, but that's exactly what we're talking about here. Standard solutions have to be accurately and exactly known. So to make standard solutions, our solute must be pure. If it's not pure, it's no good. All right. let's look at another example. Another example, I probably should have started with this one. Here I have a pile of solute. Okay, I've weighed it out and I've got 10 grams and it's pure. Okay, there's nothing else mixed in with it. That's good. But then I go to add it to my water. I'll go put it in my water, go to add it, and it won't dissolve because it's not soluble in water. We say it's insoluble. Insoluble means it won't dissolve. Now, if it won't dissolve, we haven't made a solution. So you can't have a standard solution with a solute that does not dissolve. So that's a second reason why not every substance is suitable to use as a primary standard. If they're insoluble, then that's not going to be any good to us. All right, so let's keep going. Have another look at another example. Let's say that we have a solute weighed out this time. This time it is soluble. Okay, we've got 10 grams again, but it takes us maybe 30 seconds to weigh this out accurately on our mass balance. Okay, so we've got this little pile of substance sitting on there and we're weighing it out. We're measuring it out, how many grams it is. And all this time, this substance has been reacting with the oxygen in the air. What this means is some of the particles at the surface have formed a compound. So they formed a new substance by combining with the oxygen. So now I've got 10 grams on my balance and I go and I take it and I add it to the water. Grand, primary standard, is it? Oh, sorry, is that a standard solution? I've got 10 grams of my solute dissolved in exactly 0.25 liters of solution. That seems okay. But the issue is that this substance was reacting in the time it took to measure it and put it into the solution, which means that by the time it got put into the solution, it wasn't all 10 grams of that original solute anymore, because some of it has already turned into a new substance by reacting with oxygen or water or some substance in the air. Okay, so now we might say that only 9.91 grams of the actual solute is transferred to the solution. So again, we don't know the exact concentration anymore because we don't know how much of it reacted with the air or something in the air. In this case, we would describe this solute as being now why isn't my pen writing? Sorry guys, I'm just going to pause this video for a second. The substance is not stable. So it reacted with something in the air. Okay, maybe it absorbed some water, H2O. Okay, and that added mass to so that we think there's 10 grams there, but some of it is actually water that has been absorbed. So not stable. So let's go through them again. Substances can be not pure, like this one over here, not pure. They've got other stuff mixed in with them. Then we can't know exactly 10 grams of it is added. They can be not soluble. Okay, which means they can't dissolve. You can't make a solution from them. And they also can be not stable. And if they're not stable, then we can't make standard solutions from them because they won't be accurately known. That's the key thing here. Now, substances that are not like these three things, that are perfect and they don't react, they are stable, they are soluble, they are solids, so we can easily measure them. We call these things primary, autocorrect my writing, please. We call these primary standards. Primary standards are substances which are pure, soluble, and stable. Okay, and we can use them to make standard solutions. Now, don't mix up the word standard solution with primary standard. Primary just refers to the fact that you actually make the first solution from them. Primary means first, you make the first solution from these things. Standards means that they can be used to make a standard solution. So let's go back over and look at the definition of a primary standard. Sorry. So here it is. Again, we have built into this. All right. So I want you to look at this definition here. Let's have a read of it. And then you're going to write it down in your definitions dictionary under this one up here. Okay. But read it first carefully. Okay. Underneath that in your definitions, I want you to write this down. Pure, stable, soluble. That's a phrase that can really help you in exams here. They must be pure, stable, and soluble. If one of these things gets broken, then it's not going to be good for a standard solution. Okay. All right. Now, let's look then at what are some things that are examples of primary standards and what are some things that are not examples of primary standards. Okay, so let's have a look here. We're going to write examples, and not under primary standards. So these are primary standards. What are examples of it and what are not examples of it? Well, there are two examples of primary standards on a course. The first one that we're going to talk about is sodium chloride. This is just regular salt. And sodium chloride is pure. You can buy it in a pure form. It's stable. It doesn't react with oxygen or air or moisture. And it's soluble. It dissolves in water. So sodium chloride is an example of a primary standard. Another example of a primary standard, I'm going to use a word here, okay? And I'm going to I don't like doing this. It's a complicated enough idea to get into, but we will introduce it. Okay, so the word I'm introducing here is anhydrous. We're going to break this down, anhydrous. Hydrous means with water. And in this case, anhydrous means no water. Now, what are we talking about, no water? Well, sometimes we learned before that's how crystals form. Crystals form when oppositely charged ions, positive and negative ions, form together into like what we call a crystal lattice structure. So sometimes they'll just stick together, positive and negative ones. Every second one is a positive, every second one is positive, every second one is negative. Sometimes it will be a different ratio than that. It might be 2 negatives for a positive. And sometimes, in order to form crystals, in order for these ions to stick together, or particles to stick together into a crystal, they have to use water molecules to stick together. This is called water of crystallization. So water molecules that help a crystal to bind together. I don't want to go into any more than that because it gets very complicated and it's not really that necessary here. But just know that some substances can be available in the hydrated form where they have this water of crystallization, so where water has been absorbed in the crystallization process, and they also have crystals where there's no water present, if you get what I mean. So this is one of these substances, and the substance is sodium carbonate. Sodium carbonate. So anhydrous sodium carbonate just means the sodium carbonate without the water of crystallization, without the water that's absorbed during the crystallization process. Okay, so anhydrous. So why does it have to be the anhydrous version? Well, if it's got water of crystallization, then it's not pure. It's got other stuff in there. It's not just sodium carbonate. So that's why we have to specify here that it has to be anhydrous sodium carbonate. Why is it not anhydrous sodium chloride, the one before this? It's not anhydrous sodium chloride because there's no such thing. Sodium chloride does not form any crystals that have water in them, whereas sodium carbonate does. It forms crystals that have water in them, and it can also form crystals that don't have water in it. This is the anhydrous form. That's the one we want for a primary standard. Okay, so what then are non-examples that we would have heard of? All right, so the first one is HCl, hydrogen chloride, or hydrochloric acid. Okay, but hydrogen chloride is a gas. And gases, we cannot measure accurately. You can't precisely measure how many grams you have. So it's hard to measure. Okay, so that's a non-example. H2SO4. Sorry, guys, my screen's going to crash here, so I'm just going to pause. About that. Okay, so H2SO4. This is another substance, H2SO4. And this here is what we call sulfuric acid. Now, why is sulfuric acid not suitable as a primary standard? Well, it's unstable. So as you measure it out, it will absorb water from the air. So it absorbs water as you're measuring it. So we looked at that in the diagram above. This would mean that we don't have an accurate amount of grams because by the time we measure it all out, it's already absorbed water and that's contributing to the mass. Another substance that we're going to see when we're doing our titrations is NaOH, sodium hydroxide. We've seen this before. We're going to see it when we're doing our titrations. And this is always going to be the solution we're trying to standardize. So we're going to use one of these guys to standardize one of these guys. Okay, so these we know the concentration of accurately. We use these to find the concentration of these because we can't measure them out accurately on their own. Okay, so why NaOH? Why is that not a primary standard? This is not a primary standard because it's also unstable. Now, it doesn't absorb moisture like H2SO4. Instead, it absorbs CO2. It absorbs carbon dioxide from the air. So again, it's not going to be, by the time you finish measuring it out, it's already absorbed CO2 and it's not the mass that you have measured anymore. The last one that we might see later down the line is iodine, I2. Okay, I2 is also unstable. It's unstable because as you measure it out as a solid, it's turned into a gas. So it changes directly from a solid to a gas. And that means that as you measure out 5 grams or as you measure out 10 grams, by the time you put the lid back on the container and you go to lift up the tray with the 10 grams on it, some of it has already turned to a gas in the air. So that means it's not 10 grams there anymore. Okay, so it's unstable and that it turns from solid to gas. Solid. Now, at this point, I'm gonna say we won't spend time taking down this writing, but you may want to have a look at it over here instead. Okay, so this will be neater and tidier to follow. So what are the conditions we must have for a primary standard? Here are the things. So it must be pure, stable, and solid. It must be soluble, otherwise no good. It must have a high molecular mass. Don't worry too much about that one. It just, the higher the mass, the more accurately you can measure it. And it must be anhydrous. And these here are our primary standards. So make sure you make a note of these because you can be certainly asked about what the primary standards are. And there's only 2 to remember. Okay, these are not primary standards. These are non-examples. And why? Non-examples. Most of all, it breaks one of these rules. It's not pure, it's not stable, it's not soluble, but it helps if you can explain why they're not pure, why they're not stable, why they're not soluble. So for example, H2SO4 is not stable because it absorbs moisture from the air. That's how we would say that. Okay. At this stage now, we are ready to hopefully do a few questions. So what I'm going to do is I'm going to get you guys to have a look at questions 22 to 26. And from memory, without looking back at what you've written now, so using a different copy, please, what I want you to do is I want you to have a go at these questions, please. Okay, so we've had a go at these questions. We'll quickly go through them. I'll just call out the answers. A bottle of liquid is found and stored in a science lab. It has no label. Is it a standard solution? No, it's not. Okay, it's not a standard solution if there's no label on it. And how do you know? 23. Well, we don't know the concentration. So for it to be a standard solution, I was checking here to see if you remembered the definition. It's a solution. It's one whose it's a solution whose concentration is accurately known. If you don't know anything about the solution, someone may have made it as a standard solution, but to you, it's not a standard solution anymore because you don't know the concentration. Okay, what is a standard solution? Hopefully that's the definition. Hopefully we will build into that, and without looking back, you were able to write that down. Standard solution is a solution whose concentration is known accurately. I would say that is a very common leaving cert question, very common definition. So again, like I'm putting a star beside it, maybe you should put a star beside it too. Anne says that any substance can be used to make a standard solution. Explain why Anne is wrong. Okay, so hopefully here you said something about when not all substances are pure, stable, and soluble. That would be a good start, but I would say you can improve your answer by giving examples. So examples that you know about, show off here. For example, hydrogen chloride is not a primary standard because it is not a solid and it cannot be measured accurately. H2SO4 is not stable, and that means it absorbs moisture from the air, so we cannot weigh it accurately. Again, 2 examples probably enough, but that's what you need to do to be able to get to a good standard of answer here. Okay, so you were all able to explain hopefully the first bit. Maybe now pick a couple of examples and discuss them. All right, give an example of and that's what you should always be doing in an exam question if you can, is giving examples. All right, next one, give an example of a primary standard. There's 2 of them, you choose sodium chloride or anhydrous sodium carbonate. All right, guys, that's it for this video. In the next video, we're going to discuss the steps of actually producing and preparing a primary standard solution. So we'll see you in the next one, guys.